The year is not a natural unit of time. It is an accident of where we happen to live. We built our entire concept of a year, our calendars, our agriculture, our civilizations, around the time it takes one specific rock to complete one specific loop around one specific star. That loop takes 365 days and 6 hours. We call it a year because it is the only year we have ever known. But move to any other planet in this solar system, and the year changes completely. On Mercury, it is 88 days. On Neptune, it is 164.8 of hours. The universe does not have a preferred timescale. We invented one, and then forgot that we invented it. Johannes Kepler did not forget. In 1619, working from the precise observational records of Tycho Brahe, Kepler published his third law of planetary motion. The square of a planet's orbital period is proportional to the cube of its average distance from the Sun. It is a relationship so clean and so universal that it appears in every planetary system yet observed. Kepler had no theory of gravity. He had only the numbers and the conviction that they meant something. Isaac Newton, 66 years later, supplied the mechanism. Gravity, falling off with the square of distance, pulling closer objects into faster, tighter orbits, and allowing distant ones to drift in slower, wider paths. The orbits of the planets are not a cosmic coincidence. They are a direct readout of the structure of gravitational force. For most of human history, the solar system was understood as fixed and eternal. Ptolemy's geocentric model, refined over centuries, placed Earth at the center and was accurate enough for navigation for over 1,000 years. When Copernicus proposed in 1543 that the Sun sat at the center instead, he was not merely correcting a factual error. He was dismantling a cosmology. Earth was a planet. It orbited the Sun at approximately 29.8 kilometers per second, 107,000 kilometers per hour. We feel none of it. The disruption that made the true architecture legible was Kepler's third law. For the first time, a planet's distance from the Sun could be calculated from its orbital period alone. The solar system stopped being a collection of moving lights and became a machine whose dimensions could be measured. Every number in what follows flows from that single insight. Mercury, the innermost planet, orbits at 57.9 million kilometers from the Sun. Kepler's law delivers the consequence directly. To maintain that orbit, Mercury must move at approximately 47.4 kilometers per second, 170,000 kilometers per hour, the fastest orbital speed in the solar system. It completes one full orbit every 88 Earth days. 4 Mercurian years fit inside one of ours. But Mercury's rotation is stranger still. It spins once every 59 Earth days, locked into a 3-to-2 spin-orbit resonance by tidal forces from the Sun, acting on its slightly irregular shape over billions of years. The practical consequence is extraordinary. A single solar day on Mercury, the time from one sunrise to the next, lasts 176 Earth days. 2 full years inside a single day. An observer on the surface would watch the Sun rise, move slowly across the sky, briefly reverse direction as the orbital geometry shifts, then resume, and finally set. A full cycle lasting nearly 6 Earth months. Surface temperatures swing from 430 degrees Celsius in the long daylight to minus 180 degrees Celsius in the equally long night. That is a swing of 610 degrees, with no atmosphere to moderate it. Venus orbits at 108 million kilometers, completing one circuit every 225 Earth days. But Venus rotates in the opposite direction from most planets, and so slowly that it completes one rotation every 243 Earth days, making its day longer than its year. A solar day on Venus, accounting for the interaction between its retrograde rotation and its forward orbital motion, lasts approximately 117 Earth days. An observer would see the Sun rise in the west and set in the east. The dense atmosphere of carbon dioxide and sulfuric acid clouds traps heat so effectively that the average surface temperature reaches 465 degrees Celsius, hot enough to melt lead, even though Mercury is closer to the Sun. The atmospheric pressure at the surface is 92 times that of Earth at sea level. The cause of Venus's retrograde rotation remains debated. The leading explanation is a major oblique impact early in the solar system's history. Some models suggest tidal interactions with the Sun and its own thick atmosphere could have gradually reversed the spin over geological time. Earth sits at 150 million kilometers, the distance that defines the astronomical unit, the standard baseline for measuring the solar system. Its orbital speed of 29.8 kilometers per second is fast enough to circle the equator more than 4 times per minute. The 6-hour surplus beyond the 365-day year accumulates into an extra day every 4 years. The leap year, a correction built into our calendar to stay synchronized with the physics of our own orbit. Mars orbits at 227.9 million kilometers, completing one circuit every 687 Earth days at 24.1 kilometers per second. Its day, called a sol, lasts 24 hours, 37 minutes, and 22 seconds, close enough to Earth's that Mars mission planners operate on Martian time. Its seasons are recognizable. An axial tilt of 25.2 degrees produces spring, summer, autumn, and winter on a planet with an average temperature of minus 63 degrees Celsius and an atmospheric pressure less than 1% of Earth's. Jupiter orbits at 778 million kilometers, requiring 11.86 Earth years to complete one circuit at 13.1 kilometers per second. Despite containing more mass than all other planets combined, Jupiter rotates in just 9 hours and 56 minutes, the shortest day in the solar system. That spin distorts the planet's shape measurably, flattened at the poles, bulging at the equator. The differential rotation of its cloud bands has sustained storm systems for centuries. The Great Red Spot, a single anticyclonic storm, has been continuously observed for at least 350 years and has a diameter larger than Earth. Saturn orbits at 1,432 million kilometers, completing one circuit every 29.4 Earth years at 9.7 kilometers per second. It rotates in 10 hours and 33 minutes, producing the same pronounced flattening as Jupiter. Saturn's average density is 687 kilograms per cubic meter, less than water. Its ring system extends 82,000 kilometers from its surface, but averages less than 1 kilometer in thickness. The rings are geologically young, no more than 400 million years old, and are currently being drawn into Saturn's atmosphere. In roughly 100 million years, they will be gone entirely. Uranus orbits at 2,873 million kilometers, requiring 84 Earth years at 6.8 kilometers per second. Its defining feature is its axial tilt of 97.8 degrees. It rotates essentially on its side. One pole faces the Sun for 42 years at a stretch, while the other sits in total darkness. Uranus also rotates retrograde, like Venus. Its atmosphere of hydrogen, helium, and methane reaches minus 224 degrees Celsius, making it the coldest planetary atmosphere in the solar system. Neptune, the outermost planet, orbits at 4,495 million kilometers and requires 164.8 Earth years to complete one circuit at 5.4 kilometers per second. It was discovered in 1846, not by observation but by mathematics, calculated independently by Urbain Le Verrier and John Couch Adams from irregularities in Uranus's orbit. When a telescope was pointed to Le Verrier's predicted position, Neptune was there, within 1 degree. It completed its first full orbit since discovery in 2011. Despite receiving only a fraction of a percent of the sunlight Earth receives, Neptune has wind speeds of 2,100 kilometers per hour, the fastest in the solar system, driven not by solar energy but by heat radiating from its own interior, left over from the energy of its formation 4.5 billion years ago. Pluto orbits at 5,906 million kilometers on an orbit so elliptical that it crosses inside Neptune's path at closest approach, which it did between 1979 and 1999. Its year lasts 247.9 Earth years. Since its discovery in 1930, it has completed less than one full orbit. From Pluto's surface, the Sun is a bright point. Not a disk, just a star brighter than all others, still warm enough to drive the slow sublimation of surface nitrogen ice. But nothing like what we know. The pattern is Kepler's third law made visible. Closer to the Sun, faster orbital speed, shorter year. Further out, slower speed, longer year. The relationship is exact in every case. not approximate, exact. What that means for our concept of time is harder to absorb than any of the individual numbers. Time, as we experience it, is local, the rhythm of one orbit, at one distance, around one star. On Mercury, 4 of our years pass in a single one of theirs. On Neptune, one Neptunian year spans many human lifetimes. Neither is more correct than the other. Both are precise descriptions of where each world sits in the gravitational field of the Sun. The year is not a law of nature. It is an address. It tells you how far from the Sun you are, therefore how fast you must move to stay in orbit, therefore how long your loop takes. Change the address, and every number changes. Somewhere past Neptune, in the cold and the dark where the Sun is a point of light and orbital periods stretch into centuries, the same mathematics that governs our calendar governs the ice. The geometry does not care about the calendar. It never did. It simply works, with the same precision at every distance, as it has since before the first living thing looked up and tried to count the days.